Hello and welcome to Science Unscripted. It's Connor here.
And Gabe?
And welcome to our new studio, our new Science Unscripted studio right here.
Yeah, this is awesome. Thanks to the colleagues that set this up. This is where we're going to be doing interviews when we post the videos on YouTube. This is where we're going to be doing them.
And for all the people who are listening on the podcast platforms
Right.
or in just audio form, imagine us in a
You
nice,
can watch this.
well, yeah,
if you want.
or they can imagine it. There's a black backdrop, and there's the Science Unscripted logo behind us. Anyway, welcome to the new studio. Welcome to Science Unscripted. And today we're going to be talking about what? Fasting.
Fasting. I tried it once after I tried to. I wanted to fast for like 10 days. Made it through.
Straight.
Yeah, made it through 2, and then found myself in the middle of the night gorging on Fruit Loops.
Oh my!
In the middle of the night, I took down like a box and a half of cereal because I couldn't.
Your blood sugar must have gone from what?
Yeah,
50 up to 500.
Yeah, at that point, I was a type 1 diabetic. Yeah, unfortunately, but I failed at it.
After 2 days,
Yeah.
after in a feast.
Yeah, my feeding and fasting phases got all messed up. The switch didn't work right. Because that's the science we're going to be talking about today.
Yeah, I've never ever tried fasting. I've just eaten regularly my whole life, which is part of the reason I'm really especially interested in a new study from the Max Planck Institute on Aging. It's about fish and what happens with fish. You can't always connect to humans, but in this case, there are some clear lessons for us humans to learn about when and how we should fast.
Science Unscripted.
So, hi everyone. My name is Adam Antebi. I'm a director at the Max Planck Institute for Biology of Aging in Cologne. And we recently published a paper on fasting, aging in the killifish that's gotten a lot of attention. And so we're happy to share some of our work today.
So before we talk about what happened with the fish, one thing to clarify, I think, right at the beginning is what can we say at this point at all, I guess, about fasting? Does it work? Does it cause people to lose weight? What does it actually do? And what does the research say about it?
Yeah, well, a lot of people are engaging in intermittent fasting or caloric restriction because it does have health benefits. It seems to lower blood glucose and reduce cholesterol and reduce, in some cases, age-related disease. So I think there are clear health benefits for humans and model organisms as well. The question, though, is it true at all ages and for all people?
What did you do in your experiment? You were working with fish. What did you find out?
Well, it started before us, and that is, if you look in other model systems, this is work from other people. If you look at mice and you try to do diet restriction in older age, they don't respond as well. They don't get the benefits, and it's really not understood why. And it's also true even with humans that if you lower protein early in life, you get health benefits, but later in life, it seems those health benefits seem to go away to some extent. And so we use the killifish as our model system because this fish only lives about 6 to 8 months, and we can in real time see the impact of fasting in young and old animals and the effect it has on the lifespan of the animal.
So basically, if I fast early in life, it's going to have an effect on me, usually a positive effect probably, and later in life, either not at all or not as much. And with a fish, you can do that over the course of 8 months. So later life with the fish would be their 6th month or something.
Yeah, well, we usually do it around 18 weeks so it's more like 4.5, 5 months where we start these experiments. In humans, of course, it depends what your goal is. And, a lot of people want to lose weight. Fasting or reducing calories or having intermittent fasting is a good way to lose weight. And so that's beneficial. But if your goal is to preserve your muscle, this is really where the questions start to arise. And in a young person, they can probably maintain their muscle mass. In older people, it becomes an issue because one of the things about aging is you tend to lose muscle, sarcopenia, and so fasting could have a detrimental effect. And so we really wanted to explore this in a rigorous way in these fish.
And there is generally a difference between if you fast when you're younger and if you fast when you're older, and you saw that there was a difference with these
Yeah,
fish?
so
You were looking at the latter part of their lives, and they were fasting, and the effect was the same as when they were younger. What happened with the
yeah,
killifish?
yeah. So it was really actually quite a surprise. I mean, we expected that the young fish would perform better than the old fish because young animals do better at most things. But what we saw was when we fasted young fish, there are vast changes in genes that go up and down. Um, when we looked at older animals, the number of genes that went up and down were much smaller. And we thought at first, well, maybe they just don't respond to the fasting part.
Yeah.
But actually, what we found was that they don't respond to the refeeding part, the feeding part. And they seem to be stuck in this permanent fasting trap, even though they're ingesting food. So
What
they're
what
really anabolically resistant in many ways.
what is the difference between those two phases, when I'm fasting and when I'm feeding?
Yeah.
What's
Yeah,
the difference?
great, great question. So when you're fasting, what happens is you turn down protein synthesis, which is very, you build proteins for all sorts of activities in your body. But when you fast, you tune that down because you don't have as many resources to build, right? You also suppress energy metabolism, and you also start to break down fats and glucose for whatever energy you need. When you refeed, a lot of that's reversed. You turn on protein synthesis, you turn on, fat production, and you gear up for growth,
And
basically.
so in these older fish, when they went back to feeding, to normal feeding, the protein synthesis, the fat creation or production, that just never turned back on. They stayed weak,
Well,
kind of.
yeah, it just kind of stayed weak. In fact, it seemed to, we think it actually starts it, but then fails. And what's also very interesting is when you fast those old fish, they show signs of increased inflammation above and beyond what you normally have with aging. And so this, to us, sounds like it's a detrimental effect to fast an old fish because you're increasing the amount of inflammation, and this can be detrimental to many of the tissues that you're looking at.
And in your experiment, then what did you then do? What was the point of the experiment? Just to
Yeah,
find this out in the fish, or what
well,
was the
no,
the goal?
so obviously what we really want to understand is why does it happen and what is the
Okay.
mechanism?
Yeah.
And one of the things that we discovered from our data, looking at this, how what genes were going up and down, was that there's this energy sensor called the AMP activated kinase. And this detects low energy and tries to increase the energy production so you keep things in balance. And what we noticed, so this enzyme, this energy sensor, is made of three subunits, three components. One of them is called the gamma subunit. And what we saw was quite striking, and that is that the gamma 1 subunit was going up in the fed state in young animals. The gamma 2 subunit was going up in the fasted state. So they were in this inverse relationship. So, so and with aging, the gamma 2 is always up and the gamma 1 never comes on. So we think that it's this fasting refeeding cycle that's very important for the health. You have to turn up gamma 2 during fasting and turn up gamma 1 during the feeding stage. And yeah,
And I don't know how you would do these things with a fish. Is it
yeah.
possible to take these two sliding levers, gamma 1 and gamma 2, and slide them in the older fish to make them young again? Can you do that?
Yeah, so this is why we use these model genetic organisms because we can manipulate them genetically very easily. And so our idea was, well, if the gamma one is low in an aged fish, why not activate it genetically by introducing extra copies of it and changing one amino acid in its sequence to activate it and ask what happens to the fasting response and what happens to the metabolic health
Yeah,
of the animal.
absolutely. What happens? What happened to
Yeah,
the?
so remarkably, what you see is in a young animal, they have a normal fasting feeding response. And in an old animal, they have a youthful fasting refeeding response. And it looks perfect. And they have much lower levels of inflammation. And they're able, they don't break down fat, they actually synthesize it. And most of all, their energy metabolism seems to be up.
And
They seem to
did they live longer?
Yeah, that's the most amazing thing. This one amino acid change caused these fish to live about 10 to 20% longer. And it's also not only that they live longer, but if you look in the different tissues of this fish, they look much more youthful. So, for example, if you can look at regeneration of the fin, and there's a lot more regeneration, we think, going on in those older animals. And so we think this is a really cool result. And now we have this long-lived, more healthy fish that we can study in great detail and get at more mechanisms.
Somewhere way down the line of my grandfather's is a fish. I think hundreds of millions of years ago, my great 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 was a fish. So of course, naturally, we want to extrapolate from this and say, well, what about us? Like, you said one
Yeah.
amino acid change
Yeah.
increases lifespan by 10 to 20%. That's enormous. How
Yeah.
Would that be an
likely?
invasive procedure if we
How-
did that to us?
Yeah. How and can you?
Well,
Is it
that-
even thinkable?
Well, genetically not, but maybe pharmacologically, yes. That would be one of the goals, perhaps. But let me address your question in another way, and that is this process evolutionarily conserved? Do we see the same kind of dynamics in humans? And I would say we haven't fully addressed that, but from what we can see in the data that we have looked at is that in humans, the gamma 1, like the killifish, goes down with aging. So its expression is going down with aging. And we actually did a very nice collaborative study with some of the geriatricians here at University of Cologne at the clinics. And they're looking at people and their frailty and their ability to function in old age. So they have a nice scoring system for functionality. And what we found is that if you look at the level of gamma 1 expression in those people in their blood cells, in the most frail individuals, the gamma 1 is the lowest. So when gamma 1 is low, they're the most frail. And when gamma 1 is higher, they're the most healthy. So we think it could be a biomarker for health and longevity in humans. That needs to be determined. And right now, we don't know if there's a causal effect, and there are a lot of questions that still remain to be answered. But there might be a human connection.
I know that we shouldn't compare, but if we did, and this is it's a hypothetical situation, but if the same results happened for human beings that happened for these killifish, what would they look like for humans?
Yeah. Well, I don't think we can extend our lifespan by 10 to 15% in one go, just because, killifish only live 6 to 8 months and humans live 80 years, right?
Yeah.
So
Yeah.
it's not clear that we can increase 10%, but I would guess that you could increase the lifespan and the health span perhaps by some significant number of years, maybe a few years.
And those years would we'd be healthier in those
Healthier.
yeah.
That if we infer what we've found in fish to humans, that would be the case. Now, of course, we don't know, but it remains to be tested. What's interesting, you might have heard about metformin. Metformin is an anti-diabetic drug, and it helps with diabetes, but it also reduces all-cause mortality. And metformin indirectly seems to activate this AMP kinase. So there might already be some relationship there. And so
That was my question. You used the word we could deal with this pharmacologically, which to me sounds like I pop a pill. Is that how metformin works?
yeah, Metformin is, yeah, it's a pill. It's been used to treat diabetes for years, and those people taking metformin have actually lower all-cause mortality, even though they're diabetic, than non-diabetic people. Now, we think that's a kind of a crude approach because metformin can probably activate both the gamma 1 and the gamma 2 forms of the AMP kinase. What we want to now find something that's selective for the gamma 1 activation.
Is that the
And,
next?
and, and also, what's really important is to activate this refeeding response. You know,
Yeah.
it's not just the fasting, but it's the refeeding
Yeah.
that we think is so important.
Is that the next step, Adam, or what would if you did an experiment like this on humans? What would it look like? How would you do it?
Yeah, I think before we would go to humans, well, I think what we need is a nice experimental design where we can actually measure human response to fasting and refeeding and look at what's happening to this AMP kinase and really understand, does it have a similar role in the fasting and the refeeding state, yes or no? And then do we see this kind of subunit dance going on? Yes or no? And if we do see that, then we can think about designing drugs or other interventions, maybe dietary interventions that ensure that this gamma 1 gets expressed at the right time. So it's really, you need both the fasting and the refeeding phases. They have to work in synchrony. One can't overrun the other.
And I would assume that such a trial would start with geriatric patients, with patients whose levels are all off anyway, right?
Well, I think that's a good question. We probably want to have people who are, say, 50 to 65 as those who can respond to fasting, refeeding, and those are 65 and older who might be less responsive as a comparison. I think you have to have age stratified groups, I think, to really get some insight into this. But I think the important point is that although intermittent fasting may be a good regimen for some people, I think you have to take into consideration the age of the person, how fit they are, whether they're overweight or whether they need muscle mass. All those things have to be taken into consideration. So you shouldn't just Google the internet and just take down, some intermittent fasting regimen without consulting a doctor or having some knowledge about that. But we're really just starting a lot of these studies.
And I guess as a final message to people out there who are considering fasting in the future or already doing it, is it safe to say, I mean, this is me interpreting what you've said, that after a certain point, after age 65, you shouldn't be fasting unless in consultation with a doctor, because if you're doing it, you might risk watching your own muscle mass waste away and becoming weaker. Is that fair to
Without
say?
getting anything out of it?
Yeah.
I think that's something people need to consider on an individual basis. And, it may very well also depend on how you refeed and regimen that you use for your intermittent fasting. So, yeah, I think it's very important not to just assume that it will be healthy for you until you've considered the studies and talked to a nutritionist about this. Yeah.
And that was Adam Antebi talking to us from the Max Planck Institute for Aging, which is based in Cologne, Germany. Real quick here, he wanted to especially thank the team members responsible for that study. I'm going to read them off here: Roberto Ripa, Christina Polidori, and Roman Mueller, for their work on that project.
Stress that they were the ones who did the science, that Adam was just kind of managing it. And I wanted to stress at the end a point that he made, that if you fast, you should do it in consultation with a doctor. But my next door neighbor, this guy named Jochen, he's retired.
Oh, did he not go to the doctor?
He did a phenomenal job of fasting. He's in his 60s.
What does that mean?
Well, I saw him about 6 months ago. I don't know if he's listening or watching this. Kind of pudgy.
Mm.
And then went through a fasting regimen that went on for weeks, 2 or 3 weeks, and then emerged from it. The guy's looking just like $1 million.
After 2 to 3 weeks.
Yeah.
Okay.
I think from what he said, he only had tea. That was Essentially, the only thing he had.
Wait, oh, he went full, like, no food.
He went. It was a
Okay,
long
that's
fast. This
extreme.
was not
That's extreme.
intermittent fasting.
Yeah.
And the guy, like I said, he helped me. A birch tree fell down in our backyard, and it was on his part of the yard, and he gave me the wood. He was lifting, I don't know, 200-pound portions of birch tree, so he hasn't lost the muscle. He is slimmed down.
He's not lifting 200 pounds.
Oh, with my help.
Okay.
I had one and he had the other.
Okay. So again, anecdotally, I think that it goes back to what Adam was saying. Anecdotally, fasting can do pretty amazing things. Not anecdotally. The science shows in model organisms that
certainly intermittent fasting, it has absolute effects. Cardiovascular, diabetes, metabolism, it can help you. But we don't know why yet.
But talk to your doctor in the best case before you go, especially on something as extreme as your neighbor there. And in the meantime, we can all hope that in the future there's a pharmacological option for us to get some of the benefits of fasting even into older age and maybe live longer, healthier, happier lives. That's it from us. If you have anything else to say it.
Science Unscripted.